Welcome. Make yourself comfortable. If your day has been busy, you do not need to hold it all in your mind any longer. Let your shoulders soften. Let your jaw unclench. And if it helps, let your breathing slow into a quiet, ordinary rhythm, as though you are simply listening from a safe distance. Tonight, we will drift through the solar system in an unhurried way, not as a race through names and numbers, but as a calm tour of the shapes, motions, and gentle rules that keep everything in place. And if these soft journeys through science help you settle, you are always welcome to like or subscribe. It quietly supports the channel and helps other curious sleepers find their way here too. For now, there is nothing you need to do. Just listen and let the facts pass by like distant lights. The solar system began as a thin, rotating disk of gas and dust around a newborn sun. In the earliest time, gravity gathered a cold cloud into a slow spin, and that spin naturally flattened the material like flour settling into a shallow bowl. In that disk, tiny grains collided and stuck. Then, clumps became pebbles. Pebbles became larger bodies, and larger bodies pulled in more material, simply because mass makes a deeper gravitational invitation. Over time, the disk thinned. It cleared. It separated into regions where rock could survive close to the warmth, and ices could survive farther out. The solar system, in a way, still carries the memory of that disk in the direction most planets travel, and in the shared sense of a family moving together. The Sun contains almost all the mass of the solar system. When you picture planets as the main characters, it is easy to forget how dominant the Sun truly is. Most of the solar system's substance is gathered into that single glowing sphere, and everything else is, by comparison, a delicate orbiting detail. This is why the planets move the way they do, tracing steady paths as they fall around the Sun without ever quite arriving. It is not that the Sun pulls like a hand. It is more like the Sun shapes the landscape of space and time, and the planets follow the contours as naturally as water follows a valley. Even at great distances, that quiet shaping continues. Most planets orbit the Sun in nearly the same plane, like beads on a gently tilted record. If you could step far above the solar system and look down, you would see that the major planets mostly share a common, flattened sheet of motion. This is a leftover of the original disk, preserved in choreography. The orbits are not perfectly aligned, and each world has its own slight tilt and personal variation. But the overall pattern is one of order rather than chaos. It gives the solar system a calm, architectural feel. A broad, thin arrangement, turning slowly with the Sun near the center, and the planets keeping respectful distances as they go. Gravity is not a force with a direction you can point to, but a gentle curvature that guides motion. In everyday life, gravity feels like a downward pull. In space, it is better imagined as a kind of shape. Massive objects like the Sun and planets change the geometry around them, and other objects move along the paths that shape makes easiest. This is why an orbit can be stable and serene, rather than frantic. A moon does not need constant pushing to stay with its planet. It is already traveling forward, and gravity simply bends that forward motion into a closed, repeating curve. There is something restful in this idea. Motion and balance can be the same thing, and a path can be maintained by quiet consistency rather than effort. The inner planets are built mostly from rock and metal, because early heat drove away lighter materials close to the Sun. Near the young Sun, the disk was warmer and fragile ices could not remain. The materials that stayed behind were those that could tolerate heat, like silicate rock and iron-rich metal. Over time, those substances collected into dense worlds with solid surfaces and distinct geology. It is a small reminder that planets are not just places, they are outcomes. They are what you get when chemistry meets temperature, and when distance from a star decides what can remain. The inner solar system, with its rocky planets, is like a shoreline where only the heavier grains settle. Mercury has a day that is strangely tangled with its year, creating long stretches of sunlight and darkness. Mercury is close enough to the Sun that its orbit is swift, but it rotates in a way that makes its own sunrise schedule feel unhurried. On the surface, the Sun would move across the sky at a different pace than you might expect, lingering, shifting slowly, sometimes seeming to hesitate. Without a thick atmosphere to smooth temperature, the planet's long daylight can bake the ground, and the long night can let it cool deeply. And yet, even there, the motion remains calm. The planet keeps its rhythm. It does not rush. It simply repeats what gravity and rotation have arranged. Venus turns in the opposite direction to most planets, under a sky that is bright but softly hidden. Venus rotates slowly, and its spin runs contrary to the usual direction of the solar system's main flow. The reasons are still discussed, often traced back to ancient impacts or long tidal nudges. But the result is a world with an unusual sense of time. Above its surface, thick clouds reflect sunlight so efficiently that the planet shines brightly in our sky, like a steady lantern at dawn or dusk. But from the ground, that same cloud layer would make the light feel diffused and enclosed, as though the sun were always behind a pale curtain. A planet can be brilliant from far away, and yet muted from within, and both can be true without drama. Earth's moon helps steady the slow wobble of Earth's axis, encouraging a more regular pattern of seasons. Earth does not spin perfectly upright. Its axis is tilted, and that tilt is what gives us seasons, a gentle cycling of light and warmth through the year. Over long times, a spinning body can wobble, like a top that is slowly losing its perfect balance. The moon's presence adds stability to that wobble, acting like a steadying companion through gravity. It does not freeze Earth in place, but it discourages wild swings. It supports a kind of predictability, the sort that living things can adapt to. And in the quiet background of daily life, that steadying influence continues, night after night, whether we notice it or not. Mars is home to the tallest volcano in the solar system, built by slow eruptions on a world without moving tectonic plates. On Earth, volcanoes often shift location over time because the crust is divided into plates that glide and rearrange. On Mars, the crust behaves differently. In many regions, it does not recycle itself in the same way, so a volcanic hotspot can remain under one area for a very long time. With patience, repeated flows stack up, layer on layer, building a mountain that can become immense. It is a different kind of planetary storytelling, not sudden change, but steady accumulation. Not a quick event, but a long habit of geology, slowly making something tall enough to reshape the horizon. Between Mars and Jupiter lies the asteroid belt, which is more like a wide, quiet neighborhood than a crowded field. Stories sometimes picture the asteroid belt as a place where rocks are packed tightly together, demanding careful weaving like a ship in a storm. In reality, the belt is spacious, Asteroids are separated by vast distances, and most of the time there is only emptiness between them. What makes it interesting is not density, but variety. These bodies are leftovers, fragments, and survivors from the early solar system, shaped by collisions, sunlight, and time. They keep their own small orbits, each one a faint echo of the original disk, still circling in a region where a planet never fully formed. Jupiter's gravity helps shape the solar system, acting as a kind of roaming influence on comets and smaller bodies. Jupiter is large enough that its presence is felt far beyond its own clouds. Its gravity can bend the paths of passing objects, sometimes capturing them briefly, sometimes redirecting them, sometimes nudging them into new routes that carry them inward or outward. In this way, Jupiter does not merely orbit, it participates. It is one of the reasons the solar system feels like an interacting system, rather than a set of isolated worlds. And yet, even this influence is not hurried. It unfolds over long arcs of time, through gentle deflections and repeated passages, as though the solar system were always making small adjustments to keep its overall motion smooth. Jupiter's great red spot is a long-lived storm, a swirling pattern that has persisted through many human lifetimes. On Jupiter, there is no solid surface to interrupt the atmosphere in the way mountains interrupt winds on Earth. Instead, bands of gas slide past each other at different speeds, creating shears and eddies that can organize into vast, rotating storms. The Great Red Spot is one of these, a stable swirl that has been observed for centuries. Its color and exact strength change with time, but the idea of it remains the same: a slow, circling weather system, larger than continents, turning without needing to arrive anywhere. It is motion that does not seek a destination, only a continuing balance. Farther out, the giant planets are made mostly of light elements, because colder regions allowed gases and ices to gather early. Beyond the warmer inner region, the early solar system offered colder storage. Ices could survive, gases could be captured more easily, and once a growing planet reached a certain size, it could draw in enormous envelopes of hydrogen and helium. The result is worlds that are not defined by a solid surface you can stand on, but by layers, clouds above clouds, pressure rising with depth, chemistry changing slowly as you descend. These planets are less like rocks in space, and more like deep, rotating oceans of gas, where weather and magnetism become the main architecture. And around some of these distant worlds, rings appear, not as solid hoops, but as countless small pieces moving together, each one following its own gentle orbit. And around some of these distant worlds, rings appear, not as solid hoops, but as countless small pieces moving together, each one following its own gentle orbit. Planetary rings are made of uncountable fragments that behave like a thin, flattened swarm. From far away, a ring system looks like a smooth band, almost like a painted line around a planet. Up close, it becomes something much quieter and more granular, a population of icy grains, pebbles, and larger chunks, each traveling on its own path. They keep a shared shape because gravity guides them into a plane, and because collisions, over time, tend to flatten their motion into a thin sheet. A ring is not a single object. It is a pattern made from many small motions, all agree, all repeating, all finding the same calm track around a massive world. Saturn's rings are bright because they contain a great deal of clean water ice that reflects sunlight softly. Saturn's ring system is often described as luminous, and that brightness comes largely from ice. When sunlight reaches the rings, much of it is scattered back into space, giving them a pale, gentle glow. The ice is not like a sheet of frozen lake. It is broken into pieces, and those pieces tumble and drift, turning as they go. Over time, darker dust can mix in, and the brightness can change, but the overall impression remains, a wide, delicate structure that seems too graceful for something governed by gravity. And yet, it holds its form by simple repetition, orbit after orbit, in the cold outer light. Some rings are shaped and sharpened by small moons that travel nearby, guiding particles like quiet guardians. In a ring system, a small moon can have an outsized influence. As it moves along its orbit, it gives gentle gravitational nudges to ring particles, corralling them, keeping edges crisp, and sometimes creating gaps and waves. The moon does not need to touch anything. It simply passes, and its gravity does the rest, like a subtle hand on a slow-moving crowd. Over long time, these repeated nudges add up to structure. A ring can gain narrow strands, braided-looking textures, and curved ripples, all from tiny influences applied patiently, again and again, without any suddenness. Saturn is less dense than water, a reminder that the giant planets are built mostly from light elements rather than rock. Density is an inward secret, a way of describing how much matter is packed into a given space. Saturn is large, but much of it is made of hydrogen and helium, elements that remain light even under pressure. Inside, the planet becomes stranger, with layers compressing and changing, but the overall bulk is still comparatively airy. It is a world that would not behave like a stone if you could somehow lift it. It behaves more like an enormous, self-gravitating atmosphere, wrapped around deeper, denser layers. Thinking of Saturn this way can make the solar system feel softer, as though not everything out there is hard and solid. Some worlds are made from the same materials as clouds, just gathered into a sphere by time. Titan, Saturn's largest moon, has a thick atmosphere that can carry winds and weather of its own. Most moons are airless, bare landscapes under open space. Titan is different. Its atmosphere is substantial, and it forms a protective veil around the surface. Light filters through it with a muted quality, and weather can unfold slowly, with clouds forming and drifting. Titan's air is rich in nitrogen, and it also contains organic molecules that give it a hazy, amber character. In that cold distance from the sun, familiar processes still appear in new forms. The idea of wind, of falling droplets, of seasonal change exists there too, just in a quieter register, under a dimmer sky. On Titan, rivers and lakes can exist, not of water, but of liquid hydrocarbons that flow in the cold. At Titan's temperatures, water behaves like rock, locked into ice so rigid it can act as bedrock. But certain hydrocarbons can become liquid, and those liquids can carve channels, gather into lakes, and pool in lowlands. The shapes made by flow are recognizable, even when the substance is unfamiliar. Curves of riverbeds, smooth shorelines, dark, flat surfaces where a liquid rests. It is a gentle lesson in planetary chemistry. A landscape does not belong to one material. The same physics can paint similar patterns, as long as something can flow, and gravity can pull it downhill. Enceladus, another moon of Saturn, releases fine jets of ice that drift into space and help supply one of Saturn's rings. Enceladus is small, but it is active. In certain regions, fractures in its icy surface allow material from below to escape as a spray of tiny particles. The jets rise and spread, and some of that material escapes the Moon's weak gravity, joining the broader environment around Saturn. Over time, this outflow contributes to a faint ring, a delicate halo of fresh ice. There is something tender about this connection. A moon, by quietly venting its hidden interior, can feed a structure that circles a planet far larger than itself. The solar system often works this way, with small bodies influencing big scenes through persistence rather than power. Io, one of Jupiter's moons, is the most volcanically active world we know, shaped by gravitational squeezing. Io orbits close to Jupiter, and its path is part of a complex dance with other moons. Those gravitational interactions can flex Io's interior, stretching and compressing it as it travels. That steady kneading generates heat, and the heat finds release in volcanic activity. The surface is continually resurfaced, with lava flows and deposits that change the colors and textures. It is not violent in the sense of a sudden catastrophe you must fear. It is more like an ongoing geological restlessness, powered by orbital motion. Even here, the source is simple. Gravity repeated, a gentle tug applied again and again, becoming warmth over time. Europa likely holds a vast ocean beneath its ice, protected from the vacuum by a frozen shell. Europa's surface is bright and icy, marked by long, curved fractures that crisscross like delicate lines. Beneath that shell, evidence points to a global ocean of liquid water. The idea is not of a rough sea with crashing waves, but of a dark, enclosed ocean, insulated from space, moving slowly under ice. The heat that keeps it from freezing solid may come from the same kind of tidal flexing that stirs Io, though expressed in a quieter way. If you imagine it, imagine stillness first, a smooth ceiling of ice above, a deep body of water below, and time passing gently in the dark. Ganymede is the only moon known to generate its own magnetic field, creating a small protective bubble in space. Magnetic fields often belong to planets, formed by motion in a conductive interior. Ganymede, despite being a moon, has enough internal structure and movement to produce a field of its own. That field interacts with Jupiter's immense magnetosphere, creating a layered magnetic environment, like currents meeting in a river. A magnetic field is invisible, but it is not nothing. It guides charged particles. It shapes auroras. It marks a boundary between spaces, an unseen architecture. When you think about Ganymede carrying its own magnetic presence, you are reminded that moons are not always passive companions. Some have deep interiors with their own slow, ongoing dynamics. Uranus rotates on its side, with an extreme tilt that makes its seasons feel long and unusual. Most planets spin with their axis roughly upright relative to their orbit. Uranus is tilted so far that it is as though it rolled and never fully righted itself. The result is that, over the course of its orbit, sunlight falls in a very different pattern. One hemisphere can face the sun for a long stretch, while the other rests in a prolonged darkness, and then the roles gradually reverse. It is not a sharp switch. It is a slow turning of the whole planet through space, like a lantern rotating in a large room. In that slow geometry, season becomes something drawn out and patient, more like a gradual change of posture than a brisk change of weather. Neptune's atmosphere can host powerful winds and shifting storms, even at a great distance from the sun. Neptune is far enough away that sunlight is faint, and yet the planet's atmosphere is not calm. Winds can race through its blue layers, and storms can appear, evolve, and fade. The energy for this motion comes from within the planet, as well as from the weak sunlight it receives, and it produces weather that feels like a deep, circulating engine. Seen from afar, Neptune is serene, a small blue sphere. Up close, it becomes a place of moving cloud bands and temporary dark ovals, patterns that form and dissolve without urgency. The planet turns, the air flows, and the scene continually redraws itself in slow, elegant strokes. Beyond Neptune lies the Kuiper Belt, a distant region filled with icy bodies that preserve the solar system's early leftovers. Far from the warmth, small worlds and fragments remain, orbiting quietly in the outer dark. Many are made from mixtures of ice and rock, and their surfaces can be altered slowly by radiation and rare collisions. This region acts like a deep archive, holding material that never became part of the major planets. Among these bodies is Pluto, which follows its own path around the Sun with a calm reliability, carrying a complex surface and thin atmosphere that can grow and shrink as it travels. And in that same distant neighborhood, other icy worlds continue to circle, some in tidy paths, some in slightly tilted or elongated tracks, as though the outer solar system is still gently sorting itself, even now. Far from the warmth, small worlds and fragments remain, orbiting quietly in the outer dark. Many are made from mixtures of ice and rock, and their surfaces can be altered slowly by radiation and rare collisions. This region acts like a deep archive, holding material that never became part of the major planets. Among these bodies is Pluto, which follows its own path around the Sun with a calm reliability, carrying a complex surface and a thin atmosphere that can grow and shrink as it travels. Pluto and Charon form a close pair that orbit a shared point in space, rather than one simply circling the other. Charon is large compared with Pluto, and because of that, their mutual gravity creates a balance point that lies between them, not deep inside Pluto. They move together around that shared center, like two dancers turning around a spot on the floor. This gives the system a different feel from many planet and moon pairings. It is not just a large body with a small companion. It is a partnership, a double world in miniature, bound by gravity and moving through the cold light as one. Pluto's surface includes nitrogen ice that can behave like a slow glacier, flowing gently over time. In the outer solar system, familiar substances take on new roles. Nitrogen, which on Earth is a gas in the air, can freeze into ice on Pluto, and under gravity, it can creep across the landscape in a slow, steady way. This kind of motion does not need warmth. It only needs time and a material that can deform gradually. The result is a surface that is not dead or fixed, but quietly active, rearranging itself in slow motion, smoothing some places, piling up in others, and leaving subtle hints of movement for those who look closely. Some distant worlds are classed as dwarf planets, not because they are unimportant, but because they share their orbital region with many neighbors. In the outer regions, there are bodies large enough to be rounded by their own gravity, with distinct geology and varied surfaces. Yet, the space they travel through is not cleared of other objects in the way the major planets tend to dominate their zones. The label dwarf planet is more about orbital context than about character. These worlds can still have mountains, ice plains, thin atmospheres, and a history written into their terrains. In the quiet outer dark, a smaller status does not mean a smaller story. The solar system contains resonances, where orbits line up in repeating rhythms that keep long-term patterns stable. Sometimes, two bodies settle into a relationship where their orbital periods fit together like gears. One might circle the Sun in a rhythm that regularly aligns with the other, so that their gravitational nudges happen in a repeating way. Over time, this can stabilize an orbit, or it can sculpt it, keeping bodies in certain lanes, creating gaps, or maintaining a gentle order. Resonance is not loud. It is not dramatic. It is simply timing, repeated, a kind of quiet agreement between clocks. Comets are icy bodies that can develop glowing tails when they travel inward and sunlight warms their surfaces. When a comet remains far out, it can be dark and quiet, holding volatile ices in a frozen state. As it moves closer to the Sun, that cold material can begin to release gas, carrying dust with it. Sunlight and the solar wind then shape this outflow into tails that stream away from the comet. A comet's tail does not trail behind like a banner in air. It points away from the Sun, guided by light and charged particles. Seen from Earth, a comet can appear as a soft brushstroke across the sky, delicate rather than alarming, a temporary visitor that returns to the dark when its inward journey ends. The faint glow, called zodiacal light, comes from sunlight scattered by dust spread through the inner solar system. Between the planets, there is not only empty space, but also a thin haze of small particles, grains shed from comets and collisions, drifting in broad, shallow clouds. When conditions are right, this dust can scatter sunlight and produce a gentle, triangular glow in the night sky, often seen near the horizon before dawn or after dusk. It is subtle and easily lost to city lights, but in a dark place, it can feel like a quiet reminder that the space between worlds is not perfectly clean. It holds a soft, floating residue of ancient processes. Meteors are usually tiny grains that burn in Earth's atmosphere, turning space dust into brief, harmless light. A meteor is not typically a large rock falling from the sky. Most are small, sometimes no bigger than a grain of sand. As they enter the atmosphere at high speed, friction and compression heat the air around them, and the grain itself can vaporize. The glow is the atmosphere responding, lighting up along a narrow path. What you see as a streak of light is often something very small completing its journey, returning to gas and dust high above the ground. The event is brief, and then the sky is calm again. A few meteorites do reach the ground, offering small, tangible pieces of solar system history. When a larger fragment survives the fiery passage through the atmosphere, it can land as a meteorite, often darkened on the outside by heating and cooling. These rocks can be ancient, preserving chemistry from early times. Some come from asteroids. A small number come from the Moon or Mars, launched long ago by impacts and eventually crossing Earth's path. In the hand, a meteorite is oddly quiet, dense, cool, unimpressed by human time. It sits there as a reminder that the solar system is not only a view in the sky, but also a physical place with materials that can, occasionally, arrive. The Sun continually releases a stream of particles called the solar wind, which flows outward through the planets. The Sun is not only light and warmth, it is also a source of charged particles that spill into space, forming a wind that moves through the solar system. This wind is usually invisible, but it shapes the environment around planets, interacting with magnetic fields, influencing the behavior of comets and helping define the boundary of the Sun's influence. It is a steady outflow, more like a current than a gust. Even when the night feels still, this solar wind continues to pass by, threading through space in a constant, quiet motion. The solar wind creates a vast bubble called the heliosphere, which shelters the solar system from some interstellar particles. As the Sun's particles spread outward, they push against the thin material between stars. This creates a broad region where the Sun's influence is dominant, like a moving cocoon traveling through the galaxy. Inside this bubble, the solar wind and the Sun's magnetic field help deflect certain high-energy particles arriving from beyond. The heliosphere is not a hard wall. It is more like a gradual boundary, a zone where one kind of space becomes another. It is comforting to imagine the solar system wrapped in this wide, protective flow, drifting through the Milky Way with its own atmosphere of influence. Earth's magnetic field helps guide charged particles toward the poles, creating auroras as a soft light show in the upper atmosphere. When particles from the solar wind interact with Earth's magnetic environment, some are funneled along magnetic field lines toward the polar regions. High above the surface, these particles can energize atoms and molecules in the atmosphere, which then release light as they settle back down. The result is the aurora, a slow curtain of color that can ripple and shift without urgency. It is not an explosion, but a glow, not a flash, but a drift, a quiet conversation between the sun and the air, made visible for those who happen to look up. Jupiter's magnetic field is immense, creating a vast region of trapped particles and powerful auroras of its own. Jupiter's vast rotation and deep interior help generate a magnetic field far stronger than Earth's. Around the planet, this creates a complex environment where charged particles are guided and stored, and where interactions with the solar wind and with Jupiter's moons can produce bright auroras near the poles. Even so, the overall picture remains one of steady processes, not sudden alarms. Fields, currents, and particles moving along invisible paths. A planet turning, and space around it responding, as though magnetism were another kind of weather. Tides on Earth are shaped not only by the moon, but also by the sun, with their influences combining in a gentle rhythm. The ocean's rise and fall is a gravitational effect, a stretching of Earth's water as it responds to the pull of nearby masses. The moon, being closer, has a strong influence, and the sun adds its own. When the sun and moon align in certain ways, their tidal effects can reinforce each other, and at other times they can partially cancel. The result is a pattern that feels alive but not chaotic, a repeating swell, a slow breathing of the sea, guided by celestial geometry. Even when you are far inland, the planet's water is still responding to the positions of bodies in space. Some points in space, called Lagrange points, allow objects to remain in a stable arrangement relative to a planet and the sun. In the balance of gravity and orbital motion, there are regions where a small object can maintain a consistent position, as though resting in a gentle pocket. Space agencies sometimes place telescopes near these points, not because they are magical, but because the dynamics there can reduce the need for constant corrections. It is another example of the solar system offering natural, quiet conveniences. Not every path is a struggle. Some are balanced by design, if you know where to look. Jupiter shares its orbit with groups of asteroids called Trojans, which travel ahead of and behind it in stable clusters. These asteroids are not random strays. They occupy regions where the gravitational balance allows them to remain, moving with Jupiter as it circles the Sun. Over long time, the clusters hold together, not as a solid mass, but as a community of small bodies keeping similar orbits. It is a peaceful arrangement, like a convoy that never needs to arrive. They simply continue, ahead and behind, maintaining their spacing through the subtle rules of orbital mechanics. The distances in the solar system are so large that even light needs time to travel, which makes space feel quietly spacious. From one world to another, the gap is not just a few steps. It is a broad interval where signals and sunlight must cross emptiness before arriving. This is part of why the sky can feel calm. Space is not crowded. It is mostly open, and within that openness, the planets keep their steady courses, each one a small moving point in a vast field, never rushing, never colliding, simply tracing their paths through time. Planetary orbits are not perfect circles, but gentle ellipses that bring each world a little nearer to the Sun, then a little farther away. An ellipse is a stretched circle, and in an orbit, it creates a slow variation in distance that repeats each year of that world. The change is usually not dramatic in feel, but it matters in subtle ways, influencing seasonal patterns, the amount of sunlight received, and the speed a planet moves along its path. When a planet is slightly closer, it moves a little faster. When it is slightly farther, it moves a little slower. This is not a decision the planet makes. It is simply how motion behaves under gravity, a quiet law that holds everywhere, even in the far dark beyond Neptune. And closer in, nearer to the Sun's warmth, small bodies and dust continue to drift along their own thin paths, as though the original disk never fully disappeared, only became fainter and more spread out. And closer in, nearer to the Sun's warmth, small bodies and dust continue to drift along their own thin paths, as though the original disk never fully disappeared, only became fainter and more spread out. The inner solar system is threaded with countless tiny particles that slowly spiral inward over time. Even in the spaces that feel empty, sunlight has a gentle influence. When light strikes a small grain of dust, it carries a faint push. Over long periods, that constant, delicate pressure can alter an orbit, very slowly changing the grain's path until it drifts inward toward the Sun. It is not a dramatic fall. It is a gradual settling, like fine dust in a sunbeam. The solar system is always, quietly, tidying itself, grain by grain, without any need for hurry. The Sun's light is not only brightness, but energy that warms, stirs, and sculpts the surfaces of nearby worlds. Sunlight can bake rock, loosen dust, and help drive subtle chemical changes on exposed surfaces. On airless bodies, it can create sharp contrasts between lit and shadowed regions. And it can encourage a slow kind of weathering, where atoms are nudged and rearranged over time. On worlds with atmospheres, sunlight becomes even more expressive, feeding winds, lifting clouds, and setting temperatures into gentle gradients. In all cases, the Sun is not just a lamp. It is a quiet engine, powering change through steady, reliable delivery. Mercury's surface is heavily cratered, preserving a long record of ancient impacts. Without a thick atmosphere, and without active recycling of the crust, like Earth's plate tectonics, Mercury keeps its scars. Craters overlap craters, and basins sit beside plains, telling a story that reaches back toward early, more collision-rich times. Some impacts were large enough to reshape whole regions. Others were small and left only subtle marks. The overall effect is a landscape that feels old, not in a sad way, but in a patient way, like stone that has simply been left alone. On Mercury, time is visible because so little has been erased. Despite its closeness to the Sun, Mercury has permanently shadowed craters near its poles that can preserve ice. At Mercury's poles, some craters are shaped and positioned so that sunlight never reaches their deepest flaws. In those cold shadows, temperatures can remain low enough for water ice to persist, delivered long ago by impacts or slow deposition. It is a gentle contrast. A world so sunlit and so near warmth can still hold pockets of enduring cold. The solar system often works through these quiet exceptions, where local geometry creates a private climate, sheltered from the larger surroundings. Venus's thick cloud layer reflects much of the sunlight it receives, making the planet bright in our sky. From Earth, Venus can appear as a steady, pale beacon near sunrise or sunset. That visibility comes from its clouds, which are highly reflective and spread around the planet like a continuous blanket. They send sunlight back into space, and the planet's disk shines even when it is not fully illuminated from our viewpoint. The brightness is soft rather than sharp, a smooth glow rather than a glitter. It is a reminder that what we see is often a surface of clouds, not of land, and that planets can be defined by their atmospheres as much as by their ground. Venus's atmosphere rotates faster than the planet itself, a phenomenon known as superrotation. Venus turns very slowly, but its upper atmosphere can circulate around the planet much more quickly, carrying clouds along in a swift global flow. This creates a strange sense of motion, where the sky seems to outpace the world beneath it. The mechanisms behind this include the way sunlight heats the atmosphere and the way waves and winds transfer momentum. It is complex, but the feeling is simple. On Venus, the air has its own momentum, its own habits, moving in a broad loop around the planet with a kind of persistent determination. Earth is the only world we know that clearly supports a long-standing surface ocean of liquid water. Water on Earth is not only present, but stable across wide regions and long spans of time. It collects into basins, circulates through currents, evaporates into the air, and returns as rain. That cycling helps regulate temperatures and shapes the chemistry of the surface. It also changes landscapes, carving valleys, smoothing rock, and moving minerals from place to place. There is a quiet steadiness to the idea of an ocean that has endured, not as a single unchanging body, but as a continuous process, renewing itself again and again. Earth's atmosphere acts like a thermal blanket, softening temperature swings between day and night. Air is not empty. It holds heat, it moves it, and it stores it. On a world with little atmosphere, temperatures can rise and fall sharply as sunlight arrives and leaves. On Earth, the air and water together provide moderation. Heat is absorbed and released gradually. Winds distribute warmth. Clouds can reflect light or trap it, depending on their type and height. This gives Earth's surface a kind of gentler rhythm, where night cools, but usually not to extremes, and day warms, but is rarely relentless. Earth's protective ozone layer absorbs much of the sun's harmful ultraviolet radiation. High in the atmosphere, ozone molecules interact with ultraviolet light, absorbing it and reducing the amount that reaches the surface. This does not make sunlight unsafe to notice or to enjoy. it simply changes the balance, acting as a filter that makes the surface environment friendlier for life. The ozone layer is thin by everyday standards, yet it has an outsized effect. It is another example of how small quantities, placed in the right location, can shape a whole planet's experience. The moon always shows the same face to Earth because its rotation is locked to its orbit. Over long time, gravity between Earth and the moon has arranged their motion into a stable relationship. The moon turns on its axis at the same pace that it travels around Earth, so the same hemisphere tends to face us. This is not a coincidence and not a choice. It is a natural outcome of tidal forces, slowly ironing out uneven motion until a steady pattern remains. The far side of the moon is not perpetually dark. It receives sunlight as the moon orbits. It is simply the side we do not usually see from here, quietly turning away as part of its settled rhythm. The moon's surface dust, called regolith, is created by countless tiny impacts over immense time. With no thick atmosphere to burn up incoming grains, the moon is constantly visited by small particles. Each impact breaks rock, shatters edges, and creates finer fragments. Over long periods, this builds a layer of powdery material that covers much of the surface. It is not like soil on Earth, because it contains no organic life and no water-driven chemistry. It is more like crushed stone made delicate by repetition. If you imagine it, imagine softness formed from hardness, not by decay, but by steady, patient tapping. Mars's sky can appear reddish because fine dust is suspended in its thin atmosphere. Mars has an atmosphere, but it is much thinner than Earth's. Dust can be lifted and kept aloft, and those particles scatter light in a way that gives the sky a warm, butterscotch tone. The dust also settles onto the ground, tinting rocks and making landscapes look rust-colored from orbit. The coloring comes from iron-rich minerals, altered over time. It gives Mars a consistent visual mood, as though the planet is always seen through a faint veil of its own ground, gently stirred into the air. Mars has polar caps that change with the seasons as carbon dioxide freezes and thaws. At Mars's poles, the winter cold can cause carbon dioxide from the atmosphere to freeze out onto the ground, adding to seasonal frost layers. When spring returns, that carbon dioxide can sublimate back into gas, replenishing the air. Water ice also exists there, but the seasonal breathing of carbon dioxide gives the caps a dynamic quality, expanding and contracting in a slow cycle. It is a quiet kind of seasonal weather, written not in rainstorms, but in frost and thin air. Mars's two small moons, Phobos and Deimos, are irregularly shaped, like captured fragments. Unlike the large round moons that dominate some planetary systems, Mars's moons are small and lumpy. Their shapes suggest they did not grow into spheres under their own gravity. They may be captured objects, or they may be remnants of a past impact, still debated and still studied. Either way, they feel like companions made from leftovers, quietly circling their planet without much fuss. Their orbits are close, their silhouettes are modest, and their presence adds a gentle complexity to Mars's night sky. The asteroid belt contains objects with a wide range of compositions, reflecting different birthplaces and histories. Some asteroids are rich in carbon-like materials and appear dark. Others contain more metal. Others show signs of silicates and rock. These differences are clues, hints about temperature and chemistry in the early disk, and about later mixing as objects migrated and collided. Each asteroid is a small archive, and the belt as a whole is a library without shelves, its books spread out across space. Even so, the motion remains orderly. Each object follows its own path, repeating, returning, keeping time. Ceres, the largest body in the asteroid belt, is rounded by its own gravity and shows signs of past internal activity. Ceres is not just a rock. It has enough mass to pull itself into a more spherical shape, and its surface includes features that suggest movement of materials in the past, possibly involving briny liquids. Bright patches and subtle dome-like structures hint at chemistry and flow beneath the surface, even if it is quiet now. In the middle region between Mars and Jupiter, Ceres stands as a reminder that the solar system does not divide neatly into simple categories. There are worlds within the gaps. Jupiter's cloud bands are driven by fast rotation and deep atmospheric circulation. Jupiter turns quickly, and that rotation helps organize its atmosphere into broad, alternating bands that circle the planet. Different bands move at different speeds and sometimes in different directions, creating shearing boundaries where storms can form and persist. The bands are not painted stripes. They are patterns in a moving fluid, shaped by heat rising from within and by sunlight from without. If you could watch them over time, you would see subtle changes, shifts, and small storms merging, all while the overall banded structure remains calmly in place. Jupiter radiates more heat than it receives from the Sun because it still releases energy from its formation. Deep inside Jupiter, slow contraction and lingering warmth from early times continue to produce heat. That internal energy rises and influences the atmosphere, helping drive weather systems. It is another example of the solar system carrying its past forward. A planet can still be cooling, still relaxing into its final structure, even after immense stretches of time. The warmth is not a flare. It is a slow exhale, a quiet continuation of formation. Jupiter's moons create a miniature system of their own, each with a distinct character shaped by gravity and distance. Around Jupiter, the larger moons occupy different orbital zones, and their experiences vary accordingly. Some feel stronger tidal forces, some retain more ice, some show surfaces that suggest ancient resurfacing. Together, they form a set of worlds that feel almost like a small solar system within the larger one. And yet, their motions remain smooth. Each moon keeps its path. Each orbit is a repeated sentence, spoken again and again, with small variations that slowly write their histories. And in the colder reaches beyond Jupiter, where sunlight is gentler and the pace of change slows further, the next giant worlds continue their quiet turning, wrapped in rings, haze, and long seasons, carrying their own deep interiors beneath clouded skies. And in the colder reaches beyond Jupiter, where sunlight is gentler and the pace of change slows further, the next giant worlds continue their quiet turning, wrapped in rings, haze, and long seasons, carrying their own deep interiors beneath clouded skies. Saturn's atmosphere is layered into bands and storms, but its overall appearance can feel softer than Jupiter's. From a distance, Saturn often looks more subdued, with paler tones and gentler contrasts. Part of this is the way hazes and clouds spread through its upper atmosphere, smoothing sharp boundaries. The planet still has moving bands, and it still has storms that form and fade, but the whole disk can feel like a watercolor rather than a bold painting. If you imagine standing far away in space, watching Saturn rotate, it would feel like a calm, slow reveal. a changing face, but never an abrupt one. Saturn's rings are remarkably thin compared to their width, like a broad sheet made almost flat. A ring system can stretch far from the planet, spanning a vast radius, yet remain astonishingly slender in vertical thickness. This thinness comes from the way countless particles collide and settle into a shared plane, gradually losing any up and down motion. It is a kind of natural smoothing, like a crowd learning to walk on the same level ground. The result is a structure that looks impossible at first glance. A wide disk you could almost mistake for a solid surface, when in truth it is made of separate pieces, each quietly minding its own orbit. Gaps within Saturn's rings can be created by orbital resonances, where repeated gravitational nudges clear a lane. In a ring, a particle that keeps meeting a moon's gravity at the same point in its orbit can be gently pushed again and again into a new path. Over time, this repetitive timing can empty certain regions and create distinct gaps. The clearing is not violent. It is more like a long conversation where the same message is delivered repeatedly until the particle drifts elsewhere. The gap then remains, a crisp absence that shows how rhythm and repetition can shape matter in space. Ring particles can clump temporarily into small wakes and strands, forming patterns that come and go as they orbit. Even in a ring that looks smooth, gravity and collisions can encourage short-lived structures. Particles can gather slightly, stretch into narrow features, and then relax again, like ripples that appear on a pond and fade without leaving a trace. These patterns are not permanent buildings. They are momentary arrangements made from motion itself. It is a gentle reminder that in the solar system, structure is often a living thing, maintained by ongoing movement rather than fixed material. Saturn's moon Iapetus has a striking contrast between bright and dark regions, as though one side has been dusted with soot. Some moons carry a dramatic two-toned appearance, and Iapetus is one of the most distinctive. One hemisphere is much darker than the other, likely due to the coating of darker material that reduces reflectivity and changes how the surface warms in sunlight. Over time, that temperature difference can encourage ice to migrate, reinforcing the contrast. The effect is quiet but profound. A small change in surface color can guide a slow rearrangement, and a moon can end up looking like it wears a shadowed mask. Saturn's moon Tethys is dominated by water ice, giving it a bright, clean surface in the outer light. In the colder regions, water ice can be as common as rock, and on some moons it becomes the main ingredient of the landscape. Tethys reflects sunlight strongly, and its brightness suggests a surface rich in ice, shaped by impacts and fractures. Craters sit like gentle bowls, and long grooves can stretch across the terrain, like lines drawn slowly through frozen ground. The overall mood is pale and quiet, a world where colour is subtle, and the main story is texture. Many outer moons show signs of tidal flexing, where gravity gently kneads their interiors and influences their geology. When a moon's orbit is slightly stretched, its distance from its planet changes as it travels, and that changing gravity can flex the moon's body. Over time, the repeated squeezing can generate heat. Sometimes, that heat is enough to soften ice, to encourage slow internal motion, or to support hidden oceans beneath a crust. The process is steady, not sudden. It is like bending a paperclip very slowly, but on an enormous scale, with the energy appearing as warmth within. Uranus has a pale, calm colour because methane in its atmosphere absorbs red light and leaves a cool tint behind. The blue-green tone of Uranus is not paint. It is light filtered by chemistry. Methane in the upper atmosphere absorbs certain wavelengths of sunlight more than others, and what remains is a softer, cooler hue. This gives Uranus a serene appearance, like a distant, frosted bead. Even though the planet is active in ways that are not always obvious from afar, its colour invites a sense of quiet. A calm disk in a darker part of the system, turning slowly under faint sun. Uranus's rings are darker and subtler than Saturn's, made of material that reflects less sunlight. Not all ring systems announce themselves with brightness. Uranus has rings that are comparatively dim, with particles that do not scatter much light back toward us. Some of these rings are narrow, almost like fine lines drawn around the planet. Their darkness makes them feel more secretive, as if they belong to the night rather than to the glow. And yet, they are still rings, still countless particles in orbit, still following the same rules as Saturn's, just with a quieter visual voice. Uranus's unusual tilt means its magnetic field is also strangely oriented, creating complex interactions with the solar wind. A magnetic field is shaped by a planet's rotation and interior, but its alignment can be offset and tilted. In Uranus's case, the geometry is unusual, and as the planet rotates, the field can sweep through space in an intricate pattern. This means the planet's magnetic environment does not sit neatly around it like a symmetrical shell. It moves and shifts with rotation, creating changing regions where particles are guided and stored. It is invisible complexity, the kind that exists without needing to be seen to be real. Neptune's deep blue colour also comes from atmospheric chemistry, with methane playing a role in shaping the light we receive. Like Uranus, Neptune carries methane in its upper layers, and that helps filter sunlight. But Neptune's colour can appear deeper, and the atmosphere can show more contrast in visible features. The planet's disk can present bright clouds and darker regions that shift with time, as though the sky itself is a moving painting. Even in a place where sunlight is faint, the atmosphere can express motion, guided by internal heat and fast winds. Neptune's largest moon, Triton, orbits in a direction opposite to Neptune's rotation, suggesting it was captured long ago. Most large moons form in place, sharing the same general direction of motion as their planets spin. Triton is different. Its backward orbit hints that it may have arrived from elsewhere, perhaps from a distant population of icy bodies. Over time, capture can settle into a stable orbit, but the history remains written into the direction of travel. Triton is a reminder that the solar system has not been perfectly tidy. Bodies have wandered. Some have been adopted. Triton's surface shows signs of nitrogen ice and slow geological change, even in the cold outer environment. In deep cold, certain ices behave like minerals, and they can move, fracture, and rearrange. Triton's surface has regions that look smooth and young, as if resurfacing has occurred in the not-too-distant past. Subtle activity can continue when internal heat and volatile ices cooperate, producing changes that are gentle and sparse rather than constant. A moon can be cold and still not be completely still. It can change slowly, with patience, as though even far from the sun there is room for quiet motion. Comet orbits can be stretched into long ellipses, carrying them from the outer dark into the inner light and back again. Some comets spend most of their time far away, moving slowly through cold regions where sunlight is weak. Then, as they approach the inner solar system, they accelerate, passing the Sun and swinging around it before heading outward again. This pattern creates a kind of seasonal visitor, not tied to one region, but traveling through many. The return to the outer dark is part of the cycle. The comet is not lost. It is simply following its long curve, repeating a path that can last far longer than a human lifetime. A distant reservoir called the Oort cloud is thought to surround the solar system with icy bodies far beyond the planets. Farther out than the Kuiper belt, there is believed to be a vast, diffuse population of icy objects, loosely bound to the Sun. These bodies would be so distant that they move in a realm where passing stars and the gentle tide of the galaxy can slightly disturb their orbits. Occasionally, one may be nudged inward and begin a long fall toward the Sun, becoming a comet that visits the inner system. The Oort cloud, if you imagine it, feels like a deep hinterland, a quiet halo of potential journeys. Spacecraft exploring the outer planets often rely on gravity assists, using a planet's motion to reshape their own path without extra fuel. When a spacecraft passes a planet in just the right way, it can exchange energy with the planet's orbit, changing its speed and direction relative to the Sun. The planet hardly notices, but the spacecraft can gain a new trajectory, like a careful slingshot through space. This is not a trick. It is a respectful use of orbital dynamics, a way of traveling by listening to the solar system's existing motion rather than fighting it. It is navigation as harmony, not as force. From a quiet distance, the solar system is not a collection of still objects, but a set of clocks, each keeping its own time in orbit. Every planet turns and travels with a steady cadence. Moons circle their planets. Rings flow like thin rivers of particles. Even dust drifts. Even comets trace long arcs, all within a system that rarely needs sudden correction. If you let yourself picture it, picture slow, silent movement, paths that repeat, curves that return, a family of bodies traveling together around a single star, not in a rush, not in conflict, simply continuing. And as that motion continues, inward again toward the warmer light, the smaller rocky worlds keep their own subtle changes, shaped by impacts, by sunlight, and by the slow internal settling that makes a planet feel, in its own way, quietly alive. And as that motion continues, inward again toward the warmer light, the smaller rocky worlds keep their own subtle changes, shaped by impacts, by sunlight, and by the slow internal settling that makes a planet feel, in its own way, quietly alive. A rocky planet can remain warm inside for a very long time because stone holds heat and releases it slowly. When a planet forms, it gathers energy from collisions, compression, and the gradual separation of heavier materials sinking inward. Much of that warmth becomes stored deep below the surface. Rock is not a quick conductor. It does not give up heat like metal on a winter day. Instead, warmth lingers in the interior, leaking outward over immense spans of time. That slow release can keep the mantle able to move, can feed volcanoes, and can support a planet's long, gentle geological life. From the outside, a world may look still. Inside, it can remain quietly active. A planet can separate into layers, with dense metals sinking toward the center and lighter rock forming a mantle above. As a young planet warms, its materials can begin to sort themselves. Denser substances, such as iron-rich metal, tend to sink, while lighter silicate rocks rise. This creates a core and a mantle, and sometimes a distinct crust on top, like a cooled skin. Layering is not only a physical structure, it is also a way of organizing a planet's future. A metallic core can help generate a magnetic field. A mantle can circulate slowly and reshape the surface from below. And a crust can preserve a record of what has happened, like a quiet archive. Impact craters are the most common landforms across the solar system because collisions are part of its long history. Over time, rocks and ice bodies cross paths, and occasionally they meet. When they do, the energy of the impact is released in a brief, intense moment, excavating material and leaving a crater behind. On worlds with thick atmospheres, smaller objects can burn up before arriving. On worlds with active geology, old craters can be softened or erased. But across the solar system as a whole, craters appear again and again, like punctuation marks in the story of time. Each crater is a moment preserved, made visible as a lasting shape. On airless worlds, craters can remain sharp for ages because there's little weather to soften their edges. On Earth, wind and rain gradually round mountains and fill basins. On the Moon or Mercury, there is no rainfall, no flowing river, no vegetation to hold soil, no easy erosion. A crater rim can stay crisp, and its shadows can remain dramatic. Dust may slowly settle, and tiny impacts may gently stir the surface, but the pace is quiet and slow. This is why the landscapes of airless bodies can feel stark and clear, as though time is still present, but moving with a softer touch. Earth's surface is continually renewed by plate tectonics, where large slabs of crust move slowly and reshape the planet. Earth's outer shell is not a single unbroken skin. It is divided into plates that drift over the softer mantle below. Where plates meet, they can pull apart, collide, or slide past one another. Over long periods, this motion builds mountain ranges, opens ocean basins, and recycles crust back into the interior. It also helps regulate aspects of the planet's chemistry, moving carbon and minerals through slow, planet-wide cycles. Plate tectonics is not a dramatic daily event. It is a quiet, persistent reshaping, measured in patient movement. Mars shows little sign of active plate tectonics today, which allows some surface features to remain preserved for longer. Without widespread plate recycling, large volcanic provinces and ancient terrains can remain in place without being broken apart and remade. This gives Mars a different kind of geological memory. Vast lava plains can sit beside heavily cratered highlands, and the contrast can remain visible across long time. The planet still experiences quakes and local changes, but its global surface is not constantly rearranged. There is a stillness to Mars's geology, not as emptiness, but as preservation. A planet's atmosphere can escape to space over time, especially if gravity is weak or if the planet lacks magnetic protection. Gas molecules in an upper atmosphere can, in certain conditions, gain enough energy to drift away into space. Over long periods, this slow leakage can thin an atmosphere. Solar wind and ultraviolet radiation can also strip gases more efficiently, especially for smaller worlds. The result is not an instant loss, but a gradual fading. A planet can begin with more air and end with less, simply by existing under sunlight and time. In the inner solar system, this gentle thinning has helped create a range of environments, from thick atmospheres to almost none. Mars has evidence of ancient river valleys and lake beds, suggesting that liquid water once flowed on its surface more easily than it does now. Across Mars, there are channels that branch like drainage networks and basins that look like they once held standing water. These shapes suggest that, at some time, the planet's surface conditions allowed water to move and collect. The details of that history are still studied, but the broad impression remains. Mars was not always as dry and cold as it is today. Even if the water is gone from the surface now, its past movement is written into the land, preserved in contours that feel quietly familiar. Venus demonstrates how a thick atmosphere can trap heat efficiently, keeping surface conditions very warm. Certain gases allow sunlight to reach a planet's surface, while making it harder for heat to escape back into space. When that effect becomes strong, the surface can remain heated and stable at high temperatures. Venus is an example of how atmospheric composition and pressure can dominate a planet's experience, regardless of whether the planet is similar in size to Earth. The lesson is calm but clear. A world is not only its distance from the sun, it is also the nature of the air that wraps around it. Clouds can cool a planet by reflecting sunlight, or warm it by trapping heat, depending on their properties and altitude. A bright cloud deck can send sunlight back to space, reducing warming at the surface. At the same time, clouds can also absorb and re-radiate heat, acting like insulation. The balance depends on the kind of cloud, how high it sits, and what it is made of. This is one reason that planetary climates can be subtle. A thin change in cloud behavior can shift temperatures gently over time. It is less like a switch and more like a dimmer, adjusted by chemistry, sunlight, and circulation. A planet's rotation helps shape its winds, organizing air into bands and circulating cells. When a world spins, moving air is deflected into patterns that can create trade winds, jet streams, and broad circulation loops. The exact shape depends on rotation speed, sunlight, and the thickness of the atmosphere. On Earth, this helps create familiar belts of weather. On the giant planets, fast rotation encourages strong banding. The principle is the same in spirit. Rotation does not only turn a planet, it helps choreograph its air, guiding motion into repeating flows that can feel steady and predictable. Earth's oceans store and move heat, smoothing climate by carrying warmth from one region to another. Water has a strong ability to hold heat, and oceans can transport that stored warmth through currents. This helps reduce extremes, making some regions milder than they would otherwise be at the same latitude. The ocean's motion is driven by winds, by differences in temperature and salt, and by the shape of basins and coastlines. It is slow power, patient, and continual. Even when the sea surface looks calm, the deeper system is moving, distributing energy in a quiet, steady way. The inner solar system includes many small moons that are shaped like irregular rocks, rather than rounded spheres. A body becomes round when its gravity is strong enough to pull it into equilibrium. Smaller moons often do not have enough mass for that, so they keep the irregular shapes created by their formation or by later collisions. These moons can look like lumpy potatoes or jagged fragments, quietly orbiting their parent planets. Their irregularity is not a flaw, it is a record. It tells you that they have remained small, that they have not melted into smoothness, that they carry their history on the outside. Many moons are tidally locked to their planets, keeping the same face turned inward as they orbit. Over time, the gravitational tug between a planet and its moon can settle the moon's rotation into a stable state. The result is a familiar pattern, where one hemisphere always faces the planet, and the other looks outward to space. This creates two different senses of sky. On the near side, the planet hangs in one place, changing phase slowly. On the far side, it never appears. The moon still turns through day and night, relative to the sun, but its relationship with its planet becomes a quiet, unchanging companionship. In some places, shadows in deep craters can remain cold enough to preserve ice, even relatively close to the sun. The angle of sunlight matters. In polar regions, the sun can stay low, and certain crater floors can avoid direct illumination for very long spans. Cold can pool there, and volatile substances can remain stable. This creates small, sheltered environments that differ from their surroundings, like hidden pockets of winter. It is another example of how the solar system offers gentle variety, not only through distance from the sun, but through local shape and orientation. And with those sheltered shadows in mind, the solar system's quieter details continue to reveal themselves in slow rotations and long orbits, where even a small tilt or a slight change in distance can shape an entire world's sense of day, season, and sky. The solar system is slowly changing, even when it seems perfectly still. Over long time, orbits shift by tiny amounts. Moons drift outward or inward by fractions, so small they do not belong to any one night, but to the patient unfolding of ages. Surfaces are dusted, craters are softened at the edges, and sunlight gently rearranges the chemistry of exposed rock and ice. Nothing needs to happen quickly for change to be real. In space, change is often a whisper, repeated until it becomes a new shape. Many worlds carry a faint warmth inside them, held like a memory of their formation. Even when a surface is cold and quiet, the interior can keep a slow heat, stored in deep layers and released gradually. That warmth can make ice less brittle, can allow slow movement beneath crusts, and can keep the inside of a world from becoming completely frozen into silence. It is not a roaring furnace. It is more like embers under ash, steady and long-lived. The solar system is full of these gentle reserves, hidden beneath surfaces that look calm. Light from the sun continues outward, touching each planet in its own time. Sunlight does not arrive everywhere at once. It spreads, traveling through space, reaching inner worlds quickly and outer worlds later, softened by distance. That light carries warmth and colour, and also a kind of order, marking days and seasons as it falls on turning spheres. It is the same light that makes a morning feel like morning on Earth, and the same light that glances off distant rings and pale moons. The sun's glow is constant, and yet it reaches each place as a quiet arrival. The planets keep their paths without effort, because an orbit is a form of falling that never ends. Each world is always moving forward, and always being gently drawn inward. Those two motions balance into a curve. No engine is needed, no constant push. The solar system's steadiness is made from simple things: motion that continues, and gravity that guides. When you imagine it, you can imagine the calmness of a stone circling in a slow eddy, not fighting the water, just following the shape it has already been given. Some moons are slowly sculpted by tides, in a steady rhythm that never raises its voice. A slight stretch, then a slight release, again and again over long time. That repeated flexing can warm an interior, and sometimes it can keep hidden layers from freezing solid. The story is not one of sudden breaks. It is one of persistence, a gentle kneading that, over ages, becomes geology. It is comforting to know that even far from the sun, where the light is thin, there are still slow sources of motion and change. Small grains of dust and ice continue to drift, making the space between worlds feel softly inhabited. The solar system is mostly empty, and yet it is not completely bare. There are particles too small to notice, and fragments too distant to count, moving on their own quiet trajectories. Some are leftovers from early formation, some are shed from comets, some are born from collisions that happened long before any human eye looked up. They travel in silence, and still they belong. They are part of the same family of orbits, the same shared physics, the same calm rules. Even the far edge of the sun's influence blends gradually into interstellar space. There is no sudden boundary where the solar system ends like a fence. Instead, the solar wind weakens and yields, and the environment becomes more like the space between stars. It is a soft transition, a fading of one influence into another. The solar system is not a closed room. It is a moving region, traveling with the sun through the galaxy, carrying its planets and dust and distant icy bodies along for the ride. And through it all, the motion remains unhurried. Long before any of us were here, these orbits were already underway. The planets traced their paths through darkness and light. Moons circled. Rings kept flowing, particle by particle, in thin, flattened swarms. The sun rose and set across distant horizons that have never had names. And after us, the same movements will continue. Not because anything is determined in a heavy way, but because the solar system is a stable pattern, and stable patterns tend to keep going. From where you are now, safe and still, the solar system is mostly something you feel rather than see. You feel it in the steady pull that keeps you resting on the Earth. You feel it in the moon's slow presence, even when you do not look for it. You feel it in the regularity of day and night, in seasons that come and go with gentle predictability. The solar system is not only out there, it is also here, woven into your ordinary life in quiet ways. And as the details soften, it can be enough to hold a simple picture, a small, warm world turning under a thin sky, a moon traveling with it, faithful in its rhythm, a sun shining steadily at the center, not rushing, not straining, simply being what it is. Farther out, other worlds follow their own calm routines. Some are wrapped in cloud and haze, some are etched with craters, some carry ice that behaves like rock, and rock that holds heat like a secret. Rings glide around planets in broad, quiet sheets, always moving, always returning. In the outer darkness, distant bodies circle more slowly, taking their time, as though time itself is wider there. There is no need to keep track of where each one is. You do not need to picture their exact positions. You only need the feeling of continued motion. In space, nothing is truly motionless, and yet nothing needs to be hurried. Orbits can be fast or slow, close or far, but they are all made from the same calm agreement between movement and gravity. This is why the solar system can feel soothing to think about. It is a place where repetition is not boredom. It is stability, a return, a steady pattern that does not demand attention. Somewhere above, the Earth continues to turn, carrying you gently through the night. If there are clouds, they drift and thin and gather without any need for you to follow them. If there is a moon outside your window, it keeps its quiet schedule. If the sky is clear, starlight continues to arrive, soft and patient, from far distances. And even if the curtains are drawn, even if the room is dark, the same truths remain. The motion is still happening. You can let the solar system do what it has always done. You do not need to supervise it. You do not need to solve it. The planets will keep circling. The moons will keep accompanying. The sunlight will keep traveling outward, touching surfaces, warming them slightly, then moving on. Time will keep passing in the gentle way it does, one calm moment after another. And you, here on Earth, can rest inside that larger steadiness, not as something small and insignificant, but as something safely included, a part of a system that holds together through quiet laws, a living being on a turning world, sheltered by air and gravity, with a night sky above that does not ask you to do anything at all. If your thoughts wander, that is fine. They can drift like dust in a sunbeam. They can come and go like clouds passing a distant moon. There is nothing you need to reach for now, nothing you need to remember. Only the simple comfort of knowing that outside this room and beyond it, everything continues in a calm, reliable way. The earth turns, the moon travels on, the sun shines steadily, whether you are awake or asleep. And as those quiet paths continue, you can let your own breathing find its soft rhythm. You can let your body sink a little deeper into comfort. You can let the night hold you without effort. Good night.